Imagine a universe where two particles separated by vast distances are connected in an inexplicable way. This connection is not just a theoretical concept, but a reality that has been observed and tested in numerous experiments. These particles, no matter how far apart they are, seem to share information instantaneously, defying the very fabric of space and time as we understand it. Imagine their fates intertwined, their destinies linked. When one particle changes its state, the other responds instantly, as if they are communicating faster than the speed of light. This phenomenon is known as quantum entanglement, and it challenges our conventional notions of causality and locality. This is the bizarre realm of quantum entanglement, a phenomenon so strange that even Albert Einstein, one of the founders of quantum theory, famously called it spooky action at a distance. Einstein's skepticism was rooted in the belief that no information could travel faster than light, a cornerstone of his theory of relativity. Entanglement challenges our everyday understanding of the world. In our macroscopic reality, objects have definite positions and states. However, in the quantum realm, particles exist in a superposition of states until they are observed. This duality is not just a theoretical curiosity, but has practical implications for the development of quantum technologies. It forces us to confront the limits of our intuition and embrace the mind-boggling possibilities of the quantum realm. Quantum entanglement is not just a scientific oddity, it is a gateway to understanding the deeper workings of the universe. It has the potential to revolutionize fields such as cryptography, computing, and even teleportation. For decades, scientists debated the reality of entanglement, questioning whether it was merely a mathematical quirk or a fundamental aspect of the universe. These debates were not just academic, they touched on the very nature of reality and our place within it. The resolution of these debates required ingenious experiments and a willingness to challenge established paradigms. This essay will delve into the heart of quantum entanglement, exploring its history, its implications, and its potential to revolutionize our world. We will trace the journey from the early theoretical predictions to the experimental confirmations that have solidified entanglement as a cornerstone of modern physics. From Einstein's initial skepticism to the groundbreaking experiments that proved him wrong, we will journey through the evolution of our understanding of this perplexing phenomenon. These experiments have not only confirmed the reality of entanglement, but have also opened up new avenues of research and technological innovation. Ultimately, we will grapple with the philosophical questions entanglement raises about the nature of reality itself, leaving us to wonder if the universe is even stranger than we ever imagined. Is reality a seamless web of interconnected events, or is it a fragmented tapestry woven together by the threads of quantum entanglement? These are the questions that continue to inspire and perplex scientists and philosophers alike. To grasp the essence of quantum entanglement, picture two particles. Let's call them Alice and Bob. These particles are not just any ordinary particles, they are special because they share a unique and mysterious connection that defies our everyday understanding of the world. Imagine these particles are linked in a way that defies our classical intuition. This connection is not like anything we experience in our macroscopic world. It's a bond that transcends the usual limitations of space and time. When we measure a property of Alice, like her spin, a quantum mechanical property, we instantly know the spin of Bob, even if they are light years apart. This phenomenon is not just a theoretical concept, it has been experimentally verified in numerous studies. Think of a pair of gloves, one left and one right. This analogy helps us to understand the basic idea of correlation, but it falls short of capturing the true essence of quantum entanglement. If you open a box and find a right glove, you instantly know the other box contains the left glove. This is a straightforward example of classical correlation, where the state of one object gives us information about the state of another. This is a classical correlation. It's something we can easily understand because it fits within our everyday experiences and the laws of classical physics. However, with entangled particles, the connection is much deeper. It's not just about knowing the state of one particle based on the state of another, it's about a profound and intrinsic link that exists between them. It's as if the gloves only decide whether to be left or right at the moment you open the box. This means that the properties of the particles are not determined until they are observed, a concept that challenges our classical notions of reality. This interconnectedness is independent of distance. Whether the particles are a few millimeters apart or separated by vast cosmic distances, their connection remains unbroken and instantaneous. It doesn't matter if Alice and Bob are in different rooms, different countries, or even different galaxies, their fates remain intertwined. This is one of the most mind-boggling aspects of quantum entanglement. This spooky action at a distance is what makes entanglement so perplexing and so profound. It suggests that the universe is far more interconnected than we ever imagined. It's crucial to understand that this connection is not about a signal traveling between the particles. There is no exchange of information in the traditional sense. It's about a fundamental correlation woven into the fabric of their existence. This correlation is built into the very nature of the particles themselves. Measuring one instantly influences the state of the other, regardless of the space separating them. This instantaneous influence is what sets quantum entanglement apart from any other type of correlation we know. While quantum mechanics successfully explained many observed phenomena, the concept of entanglement deeply troubled Albert Einstein. This strange phenomenon, where particles become interconnected in such a way that the state of one instantly influences the state of another, regardless of distance, seemed to defy the very principles of classical physics that Einstein held dear. He, along with Boris Podolsky and Nathan Rosen, proposed a thought experiment in 1935 that came to be known as the EPR paradox. This experiment was designed to challenge the completeness of quantum mechanics and to highlight what they saw as its fundamental flaws. The EPR paradox aimed to demonstrate the incompleteness of quantum mechanics. By presenting a scenario where two particles are entangled and then separated by a vast distance, they sought to show that the measurement of one particle's state would instantaneously determine the state of the other, suggesting that information was traveling faster than light, which contradicted Einstein's theory of relativity. Einstein believed that any complete physical theory should adhere to two fundamental principles: locality and realism. These principles were the bedrock of his understanding of the universe and the laws that govern it. Locality states that an object can only be influenced by its immediate surroundings, not by events happening arbitrarily far away. This principle ensures that cause and effect are limited by the speed of light, maintaining a coherent and predictable universe. Realism assumes that physical properties exist independently of our observation. In other words, the moon is still there even if no one is looking at it. This principle asserts that the universe has an objective reality that is not dependent on our measurements or perceptions. The EPR paradox argued that if quantum mechanics were complete, it would violate one or both of these principles. This was a profound challenge to the prevailing understanding of physics at the time, and sparked intense debate within the scientific community. Einstein proposed that there must be hidden variables yet unknown factors that predetermine the properties of entangled particles, thus preserving locality and realism. These hidden variables would ensure that the universe remained deterministic and predictable in line with classical physics. Einstein's skepticism stemmed from his deep-seated belief in a universe governed by deterministic laws. He could not accept the idea that randomness and probability were fundamental aspects of reality. He famously quipped, "God does not play dice with the universe." This statement encapsulated his conviction that the universe operated according to precise, unchanging laws, and that any apparent randomness was simply a reflection of our incomplete understanding. Entanglement, with its inherent randomness and spooky action, seemed to contradict this worldview. Despite Einstein's objections, subsequent experiments have confirmed the predictions of quantum mechanics, leaving the EPR paradox as a fascinating and pivotal moment in the history of physics. For decades, the EPR paradox remained a philosophical debate. However, in 1964, physicist John Bell devised a brilliant theoretical framework to test the validity of Einstein's hidden variables idea. Bell's theorem offered a way to experimentally distinguish between the predictions of quantum mechanics and those of any theory relying on local realism. Bell's theorem proposed a set of inequalities that would hold true if local realism held. However, quantum mechanics predicted violations of these inequalities under specific experimental conditions. This opened up the possibility of experimentally testing the very foundations of quantum mechanics. Bell's theorem was a watershed moment in the history of quantum entanglement. It shifted the debate from philosophical musings to the realm of experimental verification. The stage was set for a showdown between Einstein's classical worldview and the perplexing yet alluring world of quantum mechanics.